Exoplanet seminar. I know there's a couple of conferences happening, but thanks for coming to see this talk. I'm excited to hear about it. For the folks in the room, if you have any questions, please click on the microphone. There's an unmute button on the table around the room. But I'm going to turn it over to Rob to introduce today's speaker.
And since we have to be promptly out of the room at noon, I'll keep this short and sweet. Today we have Garrett Levine from Yale, and he's about to hopefully wrap up his PhD very, very soon. So if you have millions of dollars you'd like to throw at Garrett's way, feel free to set up a meeting with him. We actually still have some slots available. So I threw that into the Seek Slack channel. You can also email me, and we still have some available slots later today. But otherwise, going to hand it over to Garrett to talk to us about early-stage planetary processes bridging planetary and exoplanetary science. Garrett, thank you.
All right. Thank you. Can you all hear me in the room and on Zoom? In the room, yeah. Zoom.
I'll let you know this.
Okay, great. Thanks. All right. So I'm Garrett Levine. I'm a final year grad student at Yale. I'm in the astronomy department. I study topics in small bodies and exoplanets. Broadly, I'm interested in uncovering and unveiling physical processes that sculpt planetary bodies across time in their home systems. There are certain processes that happened in the ancient solar system that no longer occur here that we can see happening on exoplanets. And then there's other physical processes that we can see in the solar system at high resolution that we know must be happening in exoplanet systems. And so these two fields, traditionally planetary science and astrophysics, share a lot of overlap, especially in the realm of planetary systems. So today's topic, we'll be talking about bridging exoplanetary and planetary science, and I'll be presenting two case studies. The first one is how we can derive new insights from small bodies. Specifically, we'll talk about asteroid populations, which is crucial to unveiling the collisional physics and the dynamics that sculpt the solar system's asteroid populations. And what we'll do is we'll use the properties of Oumuamua, this interstellar interloper, this asteroid-sized extrasolar small body, to recast the solar system's minor planets in a new light. And eventually that will suggest a novel resolution to discrepant asteroid populations. And then we'll turn to exoplanets. This is a case study that's only thematically related to the small bodies, and that is this bridging planetary and exoplanet science, where we'll talk about atmospheric escape. This is something that we believe from geochemical evidence happened on early Earth and early Mars and Venus. And what we're going to do is we're going to observe this process happening on an extrasolar world. And we're going to use an approach from the solar system to probe this exoplanetary system, and we'll push towards documenting a widely known solar system atmospheric process for the first time. So without further ado, we can jump right into the small bodies part of this talk. On a sort of historical note, it's pretty fitting that I'm actually coming to you today from Yale. Yale was actually where the beginning of American asteroid science happened. It was December 14th, 1807. Judge Nathan Wheeler was out for his morning walk when he saw a fireball in the sky and heard a loud explosion. And he saw this rock crash through the side of his barn. I actually saw it last week at the Yale Peabody Museum. So not knowing what he'd seen, he called on his local university, Yale, to investigate, which at the time was mostly a divinity school. They did, however, they had just hired their first physical science professor, Benjamin Silliman. So Yale sent Silliman and a priest to look at this heavenly phenomena, where they picked up bits and pieces of the rock and they interviewed eyewitnesses. And when Silliman got back to his lab at Yale, he looked and inspected this rock, and he saw these rounded grains that today we would call chondrules. Now, he didn't recognize this as something that he'd seen on terrestrial rocks, and so Silliman correctly hypothesized that the Weston meteorite was from outer space. Now, news of this celestial event traveled down the Northeast Corridor, probably faster than I did on Amtrak yesterday, and it made its way to the sitting president, Thomas Jefferson, who said, I would believe that two Yankee professors would lie rather than believe that stones fall from heaven. So fortunately for this Yankee graduate student, attitudes towards small bodies have changed over the last couple of centuries. We now today know that stones do indeed fall from the heavens, such as the Chelyabinsk bolide that exploded over Siberia in 2013. We also see the scars from ancient impacts, such as Meteor Crater in Arizona, which motivate small bodies as a foundational component of planetary defense. Now, of course, this is a talk on science and on planetary systems, and asteroids are also crucial for these studies because mineralogy helps preserve the ancient conditions of the solar nebula. Something very relevant to Goddard, of course, is OSIRIS-REx, which visited Bennu and brought back samples, which turned out to be rich in carbon and oxygen, nitrogen, organics, and phosphates, which indicated that these key ingredients for life were likely scattered around the ancient solar system. Now, at the population level, asteroid orbits help us illuminate solar system dynamics. This is the inclination versus semi-major axis diagram of the main belt. This is kind of the radius period diagram equivalent of small body science. Now, we see that there's a lot of structure here that we can explain. For example, the Kirkwood gaps at these semi-major axis resonances with Jupiter are places that Jupiter has evacuated the small bodies. Now, we also see some dark clouds, these overdensities that are called families. And these are the collisional fragments of often ancient but sometimes very recent collisions in the main belt. And these in-progress collisional cascades can help us to understand the collisional physics that may be playing out in exoplanet systems that generate and evolve planetesimals. Now, an emergent aspect of small body science has come from the interstellar interlopers. These are small bodies that were formed in exoplanet systems and ejected into interstellar space and passed through the solar system and are detected serendipitously with the same methods that detect solar system asteroids. So these are, to date, Oumuamua and Borisov. The properties of these objects can help us understand what might be going on in exoplanet systems, and they allow us, they afford us a direct comparison between the solar system and its peers. So today's case study is going to use Oumuamua for insight on solar system asteroids. So we're going to look at the properties of this object, and then we're going to use it to recast solar system objects in a new light. So to briefly recap those properties, Oumuamua's color was this neutral reddish color. It was a bit redder than the solar spectrum, but well within the distribution of what we know in the solar system. The first clue that it was something odd was its shape, which was inferred from its light curve to be anomalously elongated. Oumuamua was likely a 6-to-1 axial ratio, which contrasts with what we would call extreme solar system objects like Geographos and Cleopatra, which are about half as elongated. Now, Oumuamua's inbound velocity also was a little bit of an oddball. You would expect that if thin disk stars like the sun were generating these interstellar objects, that Oumuamua's kinematics would also look like it were drawn from the thin disk. Instead, it would be among the slowest and thus the statistically youngest 2% of this population. Now, I showed in a paper that may be likely due to a bias in what kinds of objects pan-stars can detect, but it's nonetheless still interesting if Oumuamua may have come from some of these young stellar associations. Now, just by detecting one of these in pan-stars, you can infer that there's about 0.1 per AU cubed of these objects in the galaxy. That is, there's about 1,000 Oumuamuas inside of Neptune right now. Now, this means that all stars must eject around 20 Earth masses of Oumuamuas, which is actually commensurate with what, like, the Nice model predicts, for instance. But what's weird about Oumuamua is its size. So if we consider it to be a planetesimal and we compare it to what we consider other planetesimals to be, this figure here sort of fixes ideas on traditional theory on planetesimals, where you can see that we're considering series-sized objects. For me to put Oumuamua on this plot, I have to extend the x-axis by a factor of about 1,000. Now, of course, the solar system produces a lot of 100-meter objects, but it still sequesters most of its mass in series. And so there's some tension here between the discovery of Oumuamua, which means that there's 20 Earth masses per star of 100-meter objects, and the fact that the solar system at least puts most of its mass in big objects. Those two observations are in tension. So this may indicate that the galaxy's small body population is more bottom heavy than we expect, or more bottom heavy than at least the solar system is. Now, the properties that most galvanized the community and led to some of these very exotic hypotheses on Oumuamua was the fact that it looked like an asteroid, but it moved like a comet. It didn't have a detectable coma, but it accelerated non-gravitationally as though there were something outgassing. The direction was consistent with some outgassing that was occurring. So this is an observation that led to a lot of speculation on what types of materials or what types of bulk composition could be doing this. What could evade detection by Hubble and Spitzer while still powering Oumuamua out of the solar system? So by considering all these properties together, we can know that Oumuamua is not a direct analog to any solar system population. This led, of course, to hypotheses including some exotic ices, such as hydrogen ice and nitrogen ice, and then maybe this CO-rich exocomet that isn't like anything that we have in the solar system. So I took a look at a couple of these hypotheses, and I'll just quickly walk you through why they're probably not the case. So hydrogen ice, of course, to us astronomers sounds quite weird. We normally think of H2 as in the gas phase. And we can see why by this pressure temperature diagram. We see the solidus that delineates where the solid to vapor phase transition is. And the only astrophysical conditions that could possibly approach that solidus are these starless molecular cloud cores that are well shielded and very dense regions of space. Now, that being said, at the densities of molecular clouds, you still need to approach the CMB background temperature in order to form H2 ice. So if you do a energy balance and you ask yourself, okay, so if I consider all the sources and sinks of energy, what could theoretically happen? It turns out that the minimum grain temperature is about 1 Kelvin too warm in order to freeze out H2 ice. So it's probably impossible to even get this process started. Now, another one of these exotic hypotheses is nitrogen ice. I realize that this is, here, let me X this out. Oh, can I not do that? Okay. Oh, shoot. Okay. Well, looks like my mouse is going behind it. Okay, sorry about that. Okay, so I guess unlike H2, N2 is at least known to exist in the solar system. We have like the Sputnik Basin on Pluto, for instance, that's this large nitrogen glacier. The problem is, however, getting to 20 Earth masses of this per star is very difficult. If you run hydrodynamic cratering models to interrogate the efficiency of cratering, it ends up being a factor of about 10,000 too inefficient to produce enough 100-meter blocks of nitrogen in order to make Oumuamua a statistically likely or statistically even possible observation. So that being said, the jury's still out on the composition of Oumuamua, but in the meantime, all of these peculiarities can help us inform solar system studies. We can use these properties and we can recast the solar system's objects in a new light. And we can ask ourselves, what can we learn about our own solar system by the detection of this exoplanetesimal? So I've done this for both the anomalous elongation and this lack of a dust coma non-gravitational acceleration. And today, for this small bodies case study, I'm going to focus on the anomalous elongation and what this can tell us about the solar system and asteroid populations. So the key insight here is that aspherical asteroids have high amplitude light curves. So this means, for example, that Oumuamua's magnitude varied by about 3 magnitudes over the course of just a few hours. This light curve here comes from a dense follow-up where they were sitting on Oumuamua and observing it over several hours. But the discovery surveys that detect these objects are not sampling this light curve densely, they're sampling it sparsely. And so we can ask ourselves, did Oumuamua's shape affect its detectability? So I came into this study actually thinking that elongated objects might be easier to find, and this could be an explanation for why we found such an oddball like Oumuamua. I'll actually tell you why that is not the case. So to illustrate what this selection effect is doing and how this is affecting our surveys, let's just consider the sun, the Earth, and an asteroid. And in optical light, what we're seeing is reflected sunlight. So we're seeing parallel rays from the sun going to the asteroid and being reflected back to Earth. And what we register as the brightness is this red arc, the sky projection of this red arc. So this is the sky projected and illuminated area, and we can see as this asteroid rotates, it changes in brightness, and this can, near the limiting magnitude, changes from being detectable to undetectable. And so this is a selection effect that had been mentioned in the literature, but at the time of Oumuamua's discovery, it wasn't known even which direction it went, whether it made things easier or more difficult to find. So Oumuamua, of course, brings this to the forefront and then raises a number of questions about the solar system as well. So the way that we're going to interrogate this bias is through injection recovery simulations, where we'll make synthetic light curves, impose simulated surveys, and analyze the detection statistics. So for our synthetic light curves, we have this simple formalism for the sky projected and illuminated area of an ellipsoid, where we kept things at mostly consistent viewing geometry to isolate the shape-driven bias. So you can see some of the light curves that we generated, for example, on the figure on this slide. And if I put Oumuamua's light curve on top of this, on the most extreme one, you can see that we're doing a pretty good job with this analytic approximation. Now, I've mentioned how these simulated surveys work. So really but to give you a little bit more detail, what's really happening is we're imaging a part of the sky at a sparse cadence, maybe every 15 minutes or so. And we're observing the background stars staying in place, and we're looking for the moving objects. And those moving objects are the small bodies. And all these surveys, these sparse surveys like Catalina Sky Survey, Pan-STARRS, ATLAS, and the future LSST, they all have a characteristic cadence and a tracklet building criteria. That is, the cadence, the time between images, and the tracklet building, the number of times you need to see an object in order for the moving object processing system to link it and to detect it as a small body. So we borrowed cadence and tracklet building criteria from these contemporary surveys like Pan-STARRS and ATLAS and Catalina, and then we put it all together and we can compute our detections. So this is kind of the figure that is our main result here, where I'm plotting a heat map of the fraction of asteroids discovered versus their aspect ratio, their shape, versus the median asteroid magnitude with respect to the survey's limit, which we can just set at 0. And we can see here that darker areas are telling us where there are fewer asteroids discovered. If you can see my mouse, the dark area over here is for intrinsically faint, or for asteroids that appear generally faint. And then it goes to bright, where more asteroids are discovered as they get brighter. That's no surprise, but what we do see is we see that there's also an up to left slope here, which tells us that all else equal, as I change the shape, finding asteroids becomes less likely as they get more aspherical. Now, Oumuamua is actually off the charts here. It was about 2 times less detectable in Pan-STARRS. And so this is, of course, the opposite of what I had come into this study expecting, which is that we only found this oddball because of its shape. Instead, we found this oddball in spite of its shape. So that tells us that there's not some reservoir of spherical objects out there that we're just missing because they're harder to detect. So now we can ask ourselves, what does this mean in the context of the solar system? How can this inform us about collisional physics, and how can this inform us about the populations that constrain those collisional physics? So we found that the asteroid catalog, because of asteroid shapes, is likely biased in sizes, shapes, and rotation rates that are reported in the catalog. And these are previously unreported biases in the catalog. But from a collisional physics perspective and from a population perspective, these shapes could also be affecting the population statistics of small asteroids, these collisional fragments that come from collisions in the main belt and are transported to near-Earth space. So like many things in astrophysics, we parameterize these populations with size-frequency distributions with power laws. I'm just showing you here the cumulative number of near-Earth asteroids versus their absolute magnitude, which is a good proxy for their size. So this pink line, of course, is the known near-Earth objects, and we see that as we get to low completeness, where this kind of tapers off, the estimates from the literature on the population of small asteroids really diverge. They come apart, and there's order of magnitude discrepancies at these, call it, 50 to 100 meter sizes. So previously, this was attributed to something called trailing loss. This is essentially where, if this figure here is just an illustration of a CCD, where slow-moving asteroids deposit all of their flux at 1 pixel, but asteroids with higher angular velocities sort of smear their PSF across a bunch of pixels, and they can move so fast that they fade into the background. So all else equal, small asteroids need to be closer to Earth to be detected, and they're more subjected to these trailing losses. So this has been sort of, because there are differences in how the surveys are sensitive to different sizes of asteroids, their shutters are open for different amounts of time. People have been trying to use trailing loss to bring all of these size-frequency distributions back into agreement. I think I may have lost this. Can everybody see that on Zoom at least? Okay. That's all good, yeah. So people have used trailing loss as a way to possibly bring these size-frequency distributions together, but nonetheless, these discrepancies have persisted for decades. So the insight here is that the shapes of asteroids, if there is a size-shape correlation among asteroids, could actually manifest as these discrepancies. So the actual trend, any size-shape correlation, is unknown, and that's because this selection effect against asteroid shapes had not yet been quantified. But if you assume a size-shape correlation that's consistent with what we know in the literature, and then you inject and recover that population through our simulation pipeline, we find that the magnitude of the discrepancies in the derived power laws are similar sizes to the literature discrepancies. And so we suggest that asteroid shapes, even the much less elongated shapes that we have in the solar system, could be causing these long-standing discrepancies in the literature and could bring these size-frequency distributions back into agreement. So that's the current sort of focus. What I've been working on for small bodies is actually debiasing the size-shape correlation and then seeing at a more quantitative level if we can bring these SFDs back into agreement. So the takeaway here is that Oumuamua is providing insight on solar system asteroids that are helping us to constrain the populations that are helping us to, that are serving as very strong constraints on collisional physics. So these aspherical asteroids are hard to detect, and this bias, of course, is skewing the population statistics. So that wraps up the case study here on small bodies. I know we're about to take a turn into exoplanet land, so I want to take a moment and see if there are any questions and just give us a moment to sort of wrap up this case study. I'm also happy to take questions on it at the end, but I think it's prudent to pause here for a moment and see if there are any burning questions on this part.
Yeah, and if anyone has any questions online, feel free to raise your hand, or you can post them in chat. I actually had one. I'm not an expert on these types of observations, but when you were talking about the rotation effect and how it translates to the phase curve,
yeah,
you know, it's basically you're looking at the brightness. Mm-hmm. If we are misunderstanding the composition and there just happens to be parts of it that are very dark for whatever reason, could that be also altering what we expect to see, or how do you suss that out? Yeah, so your question is it basically, is it shapes or is it like inhomogeneities on the surface? Is it like albedo-driven inhomogeneities? And the short answer is that it could be both.
And the short answer is that it doesn't, the underlying root cause, whether it's albedos or shapes, would both manifest as selection effects against more variable light curves. We have good reason to believe that most of this variability that's in solar system asteroids and probably Oumuamua comes from shapes, which is why we focused on that. But there's also certainly an albedo component as well. So from a collisional physics perspective, understanding the contribution from albedo and shape is probably important. At present, we're assuming that it all comes from shape, and that's just based on the evidence that we have thus far.
Great, thank you so much.
All right, awesome. So with that being said, we can sort of take a step into exoplanet land, where we'll talk about a second case study on exoplanets. And specifically, we'll talk about atmospheric escape and how we're going to use solar system research to provide a new approach to exoplanets. And we're going to push towards documenting how planets respond to changes in their space weather for exoplanets. So of course, since we're trying to bridge the solar system and exoplanet science, it's prudent to start with Earth, the atmosphere that we know best. So this is a picture of Earth's atmosphere in airglow. This is taken from the International Space Station, and these are all the layers of the atmosphere that are just lit up different colors. And those different colored layers, they correspond to approximately these names and these altitudes. And what I'm going to be talking about today is analogous to the upper atmosphere, the aeronomy regime, as opposed to the meteorology regime, the stratosphere and troposphere. Now, of course, we're breathing the troposphere, and so we have a pretty good intuition for how things down here work. And I want to make a point that the aeronomy regime is a really different regime. It's a different physical regime. The gas up there is really rarefied and ionized. It's above a certain point, it's mostly hydrogen and helium. And it's really affected by what we would call space weather, as opposed to regular weather down here. Now, the International Space Station is in the thermosphere, and so we can really think of aeronomy as the transition from Earth to space. That's kind of the regime that we're talking about here. And so this study is the aeronomy regime, and most of what JWST is doing, I would classify in the meteorology regime, when it's looking for molecules that are deeper in the atmospheres. I would call that mostly meteorology, as opposed to aeronomy, which is how things are really interacting with space weather. So this is in red now the temperature profile with respect to altitude, where hotter temperatures are going to the right. And that really comes from different sources and sinks of energy. So in the upper atmosphere, what we're talking about is really the XUV absorption. This hydrogen and helium is attenuating the very high energy solar irradiation, and that's what's heating it up to these very hot temperatures on Earth, call it like 800 K. Now, if we'd like to talk about exoplanet atmospheric escape must naturally occur from the upper atmosphere, and so this puts us in the aeronomy regime. And just to give us some physical intuition for what's going on here, let's consider a sort of box of gas particles at the exobase. This is on Earth, the transition between the thermosphere and the exosphere. Now, if I have a box of gas at the exobase, this height is defined by where the scale height of the atmosphere is approximately equal to the mean free path of the gas particles. And so this is important for atmospheric escape, because if I'm a gas particle below the exobase, I generally don't traverse that, I generally don't go very far before bumping into another molecule. And so this keeps me confined to Earth regardless of my velocity. Whereas if I'm above the exobase, I really follow a ballistic trajectory. I don't really hit anything, and there's nothing really confining me to Earth. If I have the escape velocity, if my thermal velocity exceeds the escape velocity, then there's nothing stopping me from being lost to interplanetary space. So on Earth's exobase, the particles are generally going much slower than the escape velocity, and that's good for us. That means that our escape rate is only around 3 kilograms per second, And most of that actually comes from non-thermal processes like charge exchange. So here's a Maxwell-Boltzmann distribution of what the gas is really doing at Earth's exobase, where we see only the tail of that Maxwell-Boltzmann distribution is escaping. And that places us in what we would call the Jeans escape regime. Now, if I want to maximize that, or I guess minimize that escape velocity versus thermal velocity, if I want to crank up the thermal velocity, the atmosphere escape is easier when the exobase is hot and at high altitude, so less gravity pulling me down, and the planet is light and large and XUV irradiated. And so what I'm really describing here is a hot Jupiter. And this is going to be this WASP-69 planet, this hot Jupiter, WASP-69b, is going to be the target for our case study today. It's going to be a prime target for atmospheric escape. And at its exobase, the escape velocity is approximately equal to the thermal velocity, which places WASP-69 in the hydrodynamic escape regime, where the pressure gradient and the gas itself can outflow in bulk. Now, this is something that likely sculpted early Earth. There's good geochemical evidence for atmospheric escape in this hydrodynamic regime that comes from isotopic fractionation. So this is a process that we'd like to learn about, and that we'd like to study, and we'd like to constrain the energetics of this process. And I would argue that that's best done in exoplanet systems where we can observe it in action. Now, the way that we're going to constrain the energetics of hydrodynamic escape is by bringing in a solar system component, or bringing in a solar system approach. And this comes from the fact that planetary atmospheres change with stellar XUV flux. Really what we're going to try to do is understand the response of planetary atmospheres to changes in their space weather environments. How, when I change the XUV flux, how does that affect the hydrodynamic escape rate? How does that affect the planetary outflow? So on Earth, in the Earth-Sun system, the way that we understand how Earth responds to space weather is through a plot like this, or I can demonstrate it through a plot like this. This is just the sunspot count and the thermosphere power, or a good proxy for temperature, as a function of just time. I'm plotting them both against each other, this paired timeline. Now, we can, of course, see as solar activity picks up as the sunspot count increases and solar XUV activity increases, that Earth's thermosphere expands and it heats up. And this process is very well known in aeronomy, and it's something that has helped us to learn a lot about the energetics of Earth's upper atmosphere. So what I want to do is apply this same approach, these same paired timelines, and I want to create them for the WASP-69 system, our target here. We're going to take this solar system approach, and we're going to apply it to understand how hydrodynamic escape is working. Now, if you're only focused on exoplanets, I would be remiss if I also didn't mention that exoplanet aeronomy is important for explaining trends in exoplanet radii. So, of course, this is the radius period diagram here of all the short period transiting exoplanets. And we see that this striking lack of planets, or this sort of relative lack of planets, in the hot Neptune desert and the Radius Valley. And so both of these regions of parameter space it is hypothesized that hydrodynamic escape may be occurring in both of these regions. And this is our approach here, our aeronomy approach is also important for these models as well, because the changing stellar XUV is providing a natural experiment for us. We can take the approach of observing a bunch of planets at one snapshot in time, but what I'm proposing to do is observe an exoplanet as though it were a solar system object. We're going to observe it in detail through time. The star is going to change in XUV for us, and that's going to keep the planetary parameters constant, but change the input energy flux. And then we can watch as that changes the exoplanet mass loss rate, and we can use that to constrain these models of hydrodynamic escape for exoplanets as well. So this is really an approach that borrows from solar system studies to understand a physical process that's happening in our solar system, or happened in our solar system and in exoplanets. So in the solar system, we're lucky enough to observe our thermosphere and exosphere in situ. This is Earth's exosphere in Lyman Alpha from the Dynamics Explorer 1 probe in 1982. But for exoplanets, of course, we're studying atmospheres, and so we have to do this with transmission spectroscopy. So today what I'm going to be talking about is actually narrowband photometry, where we have a narrow filter around our atmospheric feature of choice. So this is really what we're doing is we can compare the transit depth in that narrowband filter where we detect the atmosphere to the transit depth in broad bands. And we can use the excess depth to tell us about the physical extent of the atmosphere. If you like to think in transmission spectroscopy terms, this is really just convolving the spectral feature across our bandpass. You can also think of transmission spectroscopy as just getting a transit depth at every resolution element. But it's really one and the same. So we're using the metastable helium feature here, which has been probed on a wide variety of planets. And broadly speaking, this is because it's optically thick at high altitude, there's no interstellar absorption, and it's ground accessible. So people like me can observe it from Palomar and Keck, as opposed to asking for HST tax, which is difficult to do. So our target, of course, is WASP-69, this planet on the edge of the hot Neptune desert. And we're going to study it over time. And we're going to be collecting atmospheric data, stellar XUV data, and then doing this over the long term. And so this is a very observant-intensive study, which is why motivating it from both a solar system and exoplanet perspectives is so important. So getting into the data themselves from our pilot study here, these are 3 light curves. One of them comes from TESS, and 2 of them come from Palomar work, the wide field infrared camera. And so in both cases, the red and the blue light curves that come from Palomar, we see that they're deeper than the TESS broadband. So that's good. That tells us that in both cases, we're detecting the atmosphere in metastable helium. Now, what you may also see is that the red and the blue lines are not equal in terms of their transit depth. And if you do the posteriors here and you sample the posterior distributions, they turn out to be 4 sigma discrepant. And so this is a strong indication that WASP-69b's atmosphere is changing with time. Now, fortunately, we're not the only ones who have observed this planet, and so we can look at a bunch of spectroscopic data, convolve it with our bandpass, and use that to compare and create a time series of WASP-69b's atmosphere over time. So you can see on the bottom plot, we can fill in our first timeline, or our first panel of these paired timeline plots. You can see the 2 Palomar points, the blue and the red here. These are the points that I was showing before. And then we have our other spectroscopic data from other instruments as well. And so now to fill in our stellar activity panel, we've been using X-ray, and we've been collecting stellar X-ray observations. Specifically, we have been using SWIFT and soon Chandra to do this. SWIFT, we got to observe for 3.5 hours or so of X-ray flux from WASP-69, the host star, via DDT, once we detected that dramatic metastable helium variability from the 2 Palomar nights. So here's what the field looks like in the optical, and here's what it looks like in the X-ray from SWIFT. So all of those red dots are a photon event, and you can see that you're probably squinting, and that's kind of the point here. If I put a circle around WASP-69, you may see a cluster of points there, but this is only a marginal detection. This is a 2 sigma, not 3 sigma significant detection. And so that seems like a bummer, but it's actually a very revealing non-detection in the presence of this archival data. So in 2016, before all of this helium business started, XMM Newton observed WASP-69, and it recorded a flux that was in the X-ray that was over twice as large as our 95% upper confidence bound from SWIFT. And so this is telling us that if WASP-69 were doing in 2023 what it was doing in 2016, we would have actually detected this at about 4 or 5 sigma. Instead, you can see that the star is clearly there's been some change in X-ray over time. And so because the 2016 XMM Newton data was not at the same time as any of the helium data, we can't link them directly, but what we can do is we can link them via modeling. We can ask ourselves, is that change in X-ray flux consistent with something that could be driving that outflow and driving the changes in that outflow? So really what we're going to do here is we're going to create a new figure where we're taking the two y-axes of our paired timeline plots, and instead of relating them with time, we're going to plot them against each other, and we're going to relate them with modeling. So our one point of contemporaneous data comes from 2023. This is our Night 2 Palomar data and our SWIFT data. This is our upper bound on SWIFT and our atmospheric detection from Palomar. Now, if I draw a bunch of atmospheric models that go through that point, and then I vary the X-ray output, and I ask myself, what happens to the expected transit depth from Palomar work, I can then put on top of that not another point because we don't have data at the same time, but I can put two sets of error bars, basically, or two sets of 1 sigma confidence bounds. And what I see, actually, is that to explain the variability from 2019 to 2023, the X-ray flux of WASP-69 would have needed to vary by another factor of 2 or so. It would have needed to vary by a factor of 6 or so over that time scale. Now, that is actually very consistent with what we expect sun-like stars, and especially K stars like WASP-69, to be doing. And so we can say that it's plausible that these changes were driven by the variability, the X-ray variability of this star. So sort of the takeaway from this pilot study here, the fine-grained one, is that we're trying to trace years-long changes in this thermosphere with changes in stellar XUV. At the population level, we're probing this cause and effect process that may be playing out in the exoplanet demographics. And then at the big picture, we're connecting this research with geoscience and bringing this flourishing field of aeronomy to the exoplanets. Now, of course, looking ahead, what we would really like is we would like more points on that modeling plot. We would like to relate points not just with 1 sigma error bars, but we would like multiple points to relate with modeling, because that can constrain the energetics of the hydrodynamic escape. So really, we'd like to build out the aeronomy time series across this activity cycle, and we're well on our way to doing so. We just collected more SWIFT cycle 21 data on this planet, and we have actually, as of yesterday, just got our Chandra time scheduled to observe this target this winter. Now, we've also been looking, we've been following this up with Keck and Palomar, and we have several more metastable helium data points to plot with our contemporaneous X-ray data. And so hopefully the next time I chat with you, I can show you some refined analysis and results from this study. We've also been collecting these data simultaneously with TESS, which gives us a long time baseline in broadband photometry, and it allows us to really pin down stellar activity in that epoch. We're also looking into other indicators of stellar X-ray activity or XUV activity. Specifically, we've been using Apache Point to build out the R prime HK time series over time. We've just been getting short spectra over time and building out that R prime HK activity time series. Now, something else that I want to mention while I'm here, especially at Goddard, is the fact that we've also been doing this in conjunction with the Exoplanet Watchers. So, of course, this is something very near and dear to Rob. We've been involving Exoplanet Watch to monitor transits in broadband when we can't observe with TESS at the same time. And that's important, as I mentioned, because this helps us constrain stellar flares, which can change the atmospheric escape rate on timescales of hours to days, the transit timing as well. Some of these planets have asymmetric transits because they have ram pressure sculpted clouds of escaped gas. And so that doesn't lead to a very good Palomar transit time, but that can be refined in broadband through these exoplanet watchers. Also, this helps us with baseline issues and with star spots as well. And so you might ask yourself, okay, so we have exoplanet watchers with small backyard telescopes, but how can they possibly be competitive with me at Palomar with my 5-meter telescope? And the key insight is that because I'm using a narrow filter, the exoplanet watchers are actually collecting an almost exactly the same number of photons as I do. I let through about 0.02% of the light that's hitting the telescope, whereas they're letting through about 20% in a normal broadband filter. And so that leads to light curves for me with Palomar that have about the same sized error bars as the exoplanet watchers do. And so this lets us actually use their data in a very relevant manner to the atmospheric studies that I'm doing with Palomar. So this is a great way. I've really enjoyed chatting with Rob and working with him on Exoplanet Watch and getting them involved in this research. And I'm hoping to continue to do so in the future. Now I'm also working on some James Webb work with atmospheric escape. When I said that James Webb does mostly what I would call planetary meteorology, there is a case for exoplanet atmospheric escape with JWST, and that's because nearest SOS actually covers the metastable helium triplet in a single resolution element, 2 pixels. And so I'm part of the TUNE study that's led by Shreyas Visapragada at Carnegie Science. And what we're doing is we're homogeneously analyzing all of the data with nearest SOS that covers this metastable helium triplet. And this will help us, for me, to identify good targets for future aeronomy work and provide us with a homogeneous population-level catalog of atmospheric escape. So with that, that kind of wraps up the second case study. And I'd be happy to take any questions on the helium work or on the small bodies part at this point. I'd just like to say thanks for your attention and thanks for joining me. I know it's a very busy week for a lot of people, so thanks for coming.
Garrett, that was awesome. Oops. Yep, that was awesome talk and 2 very different projects, but really cool work on both of them. So yeah, we have time for a couple of questions. So anyone online, feel free to raise your hand, or of course anyone in the room is welcome to. Yeah, just if you don't mind clicking that, online can hear you.
Awesome, great talk. I am particularly interested in the ESCAPE project, but learning about Oumuamua was also cool. And I also like that you brought attention to how important it is to incorporate high energy radiation in interpreting exoplanet atmosphere science. My question is for helium escape and looking at XUV or connecting XUV variability with outflow variability. For helium in particular, the metastable population requires a very specific set of conditions, and I was wondering, can you directly back out the fact that the variability in the helium 10830 transit is because the outflow is changing or because the population is changing?
Yeah. So that's a great question. And I think what you're hitting at is that there's a degeneracy between the radiative transfer and the hydro. When you change X-ray, presumably you change the EUV, and that changes the level populations as well. So that's something that we can only do with modeling. So recently, or what we've been doing is we've been using power laws from King et al. 2018 that you can use to extrapolate from X-ray to EUV fluxes. Doing other ways of spectral extrapolation or spectral interpolation, depending on where your wavelengths are, is something that we would really like to do, and it would be great to chat with you about that. So it's definitely, yeah, the degeneracy is something that we can, at this point, because there's nothing in the sky that can observe FUV spectra, is something that we can only do with modeling. We think that we're doing an okay job with it. The model that we have, PWinds, incorporates both hydro and radiative transfer, so it's not something that we're glossing over. It's something that we're changing in the model as well when the X-ray changes.
Anyone else have any questions? Yeah, go for it, Rob.
Really awesome talk, Garrett. So other than sort of looking into like the whole alien idea for Oumuamua, what's sort of the prevalent theory right now for why did they increase acceleration? You provided those 2 examples. They both have their own very large challenges. Is outgassing still what the community sort of is focusing on and things the main reason that caused the acceleration?
Yeah. So I would say there's the outgassing hypotheses of something weird happened and we didn't detect it, either some unknown substance that we didn't look for, or some people have proposed that it was just this very light object that was propelled by radiation pressure. That would mean that it would have to be less dense than the air in this room. So I think that's a little difficult to do. And then there's, of course, the light sail, that radiation pressure hypothesis. So at present, I don't think that there's a consensus right now. The way that you could make it work with solar system volatiles is what I call the shy Oumuamua hypothesis, and that it was accelerating non-gravitationally, but it just wasn't outgassing when we looked. We know that some comets accelerate sporadically, and they outgas sporadically. It's a little fine-tuning, but that's, for example, one hypothesis that I didn't mention. So yeah, the jury's still out. I think that Rubin should detect on the order of 10 of them, and so that's hopefully something that we can follow up and we can understand what's going on.
Our knowledge of Oumuamua is still pretty limited, right? Like, we just know the shape, we don't know the density or the...
Right.
Do we know the albedo at all?
Mm-mm.
So,
Nope.
Lots of unknowns still.
Yeah. Mm-hmm.
Probably not a light sail, though.
Right, yeah.
Cool. Thanks, Garrett. Appreciate it.
Well, I think the director of all of Goddard Science is breaking down the door, so we might end a little bit early with that. But Garrett, I think, is around later today, so if anyone has any other questions or wants to talk more, please feel free to get in touch with Rob or me, and we can get you in touch. But thanks. Let's thank Garrett again for the great talk. And thanks, everyone, for coming out today. I'm going to end the meeting now. Yeah, of course.